Hello and welcome. In this video I'll be talking about some of the fundamentals of probability, including some vocabulary, some techniques for calculating probability, and then several examples. So let's jump in with some of the vocabulary. Any process with an uncertain outcome can be considered a probability experiment. So if the outcome is certain, then there's no probability involved. So that's a key thing here. And so, a simple example of an experiment would be flipping a coin, where the outcomes could be heads or tails. And each time that you flip that coin, you're not sure what's going to happen. You know it's going to be one of two things, but you can't be certain which of those two things it will be. But an experiment could be, like when you're polling conducting a poll, and you randomly select someone and ask their opinion on something, and maybe it's a yes/no question. You're not sure what they're going to say, and so that can be considered an experiment. Another vocabulary term that comes up in probability is sample space. So the sample space, and usually we're going to use a capital S as an abbreviation for this, is the set of all possible outcomes of an experiment. So in the example I gave of flipping a coin, the sample space would be those two possible outcomes. Usually we refer to them as heads or tails. If you were conducting a poll and asking a yes/no question, then those possible answers, the possible responses, yes and no, would be your sample space. An event, and we often use a capital E for this, is a subset of S. Although I want to point out, there's nothing special about this letter E. Sometimes if you have different events, you're going to have to use different letters, and so we usually do use a capital letter. We'll reserve the use of S to mean the entire sample space, but E would be some subset. Now, usually we mean a proper subset, so not the entire sample space itself. A simple event could be a single outcome, but all right. And I'll show you some examples of how I can construct a subset from a sample space later on in this video. So the point here is to discuss probability, and so I want to talk about one method for computing probability, and this is for theoretical probability. So if an event E has N of E, so this would be the number of outcomes that are in that event E. So if an event has this number of equally likely outcomes, and its sample space, S, has N of S, so that would be, when we see this notation of a lowercase n and then something in parentheses, it's the count. So this is the number of outcomes that are in the entire sample space. So if the sample space has this certain number of equally likely outcomes, the theoretical probability of event E, denoted P of E, so that's a capital P with the E in parentheses, it's a quotient here. It's the number of outcomes in E divided by the number of outcomes in S. So we could simplify this and say the number of things in E using this notation N of E over N of S. So this is how we can calculate the theoretical probability for an event E. So let's look through some examples. I'm going to take this away, and of some common probability experiments, and how we can discuss the sample space and construct events, and what the probability of those events might be. So when the experiment is to flip a coin, the sample space S consists of the outcomes heads and tails. So we often use set notation, and so where we just list the elements, and that's certainly convenient to do here when there are just these two elements. Now, as far as events go, I would be looking at subsets here. There are really, besides the entire set itself, there are two outcomes which we could refer to as simple events, one of them being heads and tails. And so the probability for each of these, so if we want to say the probability of heads, so that's 1 of 2 possible outcomes. So 2 is the number of things in the sample space. 1 is the number of outcomes that are in this event. And so that has a probability of 1/2. And if you prefer, you could use a decimal, or sometimes people prefer to use percentages. There's a 50% chance of that happening. And also, of course, that would be the same for tails. So what about when you roll a die? So here I'm talking about a standard 6-sided die. There are other die with different number of sides, but this is just a standard 6-sided die. So here the sample space S is the set of whole numbers. Actually, the whole numbers 1 through 6. So when we construct an event, so maybe I want to say E is the even numbers. And so when I talk about the probability of E, that is the number of things in E over the number of things in S. So there are 1, 2, 3 even numbers and 6 numbers altogether. So this also has a probability of 1/2. I might construct a different event. I'll call it F, and this has the elements for, let's just say, 5 and 6. And so the probability associated with event F is 2 out of 6, or 1/3. Let's just do one more. I'll do event G, and this is a number greater than 2. So by that, I would mean a number greater than 2. If I'm talking about strictly greater than, it would be these outcomes, and there are 4 of those out of the 6 possible, and so that is 2/3. I want to point out, in probability, if something is guaranteed or certain, it has a probability of 1, or 100%. If something is impossible, it has a probability of 0. So if I wanted to ask for the probability that I would get a roll less than 10, that's guaranteed. All of the possible outcomes in S are less than 10, so that would be a probability of 1. So let's move on to another experiment where we flip a coin 3 times. And so to help us determine the sample space, I'm going to use a tree diagram. So on the first flip of a coin, a person could get heads or tails. I'm just going to use H and T to represent those possibilities. And on a second flip of a coin, once again, you have these possibilities of heads or tails. And of course, those are the same on the third and final flip of the coin. And so I'm looking at the possible sequences to determine my sample space. So I could get heads, heads, heads. That'd be this first sequence. Heads, heads, tails. Heads, tails, heads. Head, tails, tails. I'm going to just continue down here. Tails, heads, heads. Tails, heads, tails. Tails, tails, heads, and then tails, tails, tails. And so that's the sample space when I'm looking at the possible sequences. It's really important to be clear on what it is that you are using this experiment to determine. Now, if I were to flip a coin 3 times and count H's, then the sample space would be different. In that case, the possibilities, the number of heads would be 0. So that would be, for this guy, when I would get tails, 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 and 1. So that would be here, here, and here. I could get 2 heads, so that's here, here, and here. Or I could have all 3, which would be this first sequence that's listed. So, each of these sequences is equally likely. So, I can consider each of these to be an event. So this event of 0 H's corresponds to this one outcome. This event occur corresponds to 3 possibilities. So if I'm using this experiment where I'm rolling, flipping a coin 3 times and counting H's, the probability of exactly 1 head, so I'll just say of 1. Well, in that event, there were 3 sequences out of the 8 possible sequences. So that has a probability of 3/8. All right, so lastly, let's look at another common probability experiment. What if you're going to roll not just a single die, but a pair of dice, and you want to consider the possibilities? So because it's a little tedious and time-consuming, I went ahead and just listed out the possible combinations. I have done this in a table that's 6 by 6, and so here would be one possibility where you have a pair of 1s, and at the other end of this table have a pair of 6s. But these are all the possible combinations, and these are, in fact, equally likely. So this is the entire sample space. So N of S is, in fact, 36 here. So if I wanted to know, let's see, the probability of doubles. So that would be an event where I had 2 of the same thing. Those are on the diagonal. And so there are 6, sorry, I circled the wrong one. There are 6 equally likely outcomes in that event, and there were 36 equally likely outcomes in the sample space, so this is 1/6. What if I wanted to know the probability that the dice sum to 7? Well, those actually are on the other diagonal. And there are 6 of those pairs that sum to 7. Those are all equally likely. That's 6 out of 36. And again, I equal 1/6. What about, let's do one more. The probability that you have at least 1 4. And so get another color here. So at least 1 4. That includes all of these guys. So those have a 4 followed by a 1, 2, 3, 4, 5, or 6. And then if we look on the other way, we have these. And I just want to be careful that I don't double count the double 4s. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there are 11 pairs that include at least 1 4, and that's out of the 36, and those are equally likely, so that has a probability of 11 out of 36. All right, so I hope that helps with some of the fundamentals of probability, with the some of the language that we use in probability, and then also how we can calculate theoretical probability. All right, I'll see you next time.